In this video, we're going to talk about two key measurements we make when we're dealing with DC circuits, one being potential difference and the other one being current. Potential difference is defined as the work done in moving a unit positive charge from one point to another. And sometimes we call potential difference the voltage. The equation for potential difference gives us V is W over Q, where V is the potential difference measured in volts, work is the work done in joules, and Q is the charge in coulombs. So what this tells us is that a volt is a joule per coulomb. Current is the rate of flow of charge. And so the way we measure that is the amount of charge passing through a given point in a given time frame. The equation for current is given as I is delta Q over delta T, where I is the symbol for current, and current is measured in amperes. Delta Q is the charge passing through, and delta T is the time passing in seconds. And so what this tells us is that an ampere is also defined as a coulomb per second. There are many different analogies for potential difference and current. Some people use water to describe it, or some people use gravitational potential energy. There's a lot of different great analogies. The thing I want to point out, and I think this is the key idea of this video, and the thing, if you remember one thing from the video, this is probably the most important. This will help you a lot in the future. If you remember that potential difference is related to the energy of the charge carriers, so how much energy they have, and then current is related to how many charge carriers, the number of charge carriers. And if you can distinguish that in your mind, it's really going to help you solve when we get to more complex circuits. So again, potential difference is the energy, and current is the number of charged particles. Way back when we started working with electricity, we didn't really know about protons and neutrons and electrons. Those particles hadn't been discovered yet. And it was just assumed that the positive charge was the thing that was moving around the circuit, giving everything the energy. What happened is we defined all of our laws and all of our formulas and all of our equations using this idea that the current is going from the positive to the negative side of the terminals of the battery. Now that we know what an electron is, we know it's the electron actually moving. But we have all this established physics already with the positive charge moving. And so when we talk about current, what we're talking about is the flow of positive charge. So this is a bit of a confusion here, and we're going to have to distinguish this in our mind. But when we talk about current, we're really talking about conventional current. And so conventional current is the imaginary flow of positive charge. We know in reality electrons are the ones moving, but when we do these calculations and we solve these problems, we're assuming the charge is going from positive to negative. If we want to measure potential difference, we use a thing called a voltmeter. And the idea is the voltmeter can attach inside of a circuit, and it can measure how much energy a particle has before and after it passes the points on the voltmeter. So what we really want is we want to make sure that no charge goes through the voltmeter. We just want the charge to go past it, and it can measure the amount of energy it loses in that distance. If we want to measure the current, we use what's called an ammeter. And an ammeter, we want all the charge carriers to pass through because an ammeter is essentially just going to count how many charged particles pass through it. So you want all of them to go through it. Now, in a previous video, I talked about EMF, which is electromotive force, and PD. Now, they are very similar. They're calculated the same way, and the definitions are quite similar. PD and EMF both are work done over Q. The difference being EMF is what is the energy provided to the circuit from the cell or the power source, whereas potential difference is the components in the circuit using that energy to do something else. Sometimes they use it for heating or light or whatever. So the key difference here, what we need to keep in mind, is that EMF is the amount of energy provided, so that's coming from the battery, and voltage is the energy being used, so that's used by objects in the circuit. Both have a unit of volts. PD is measured in volts and EMF is measured in volts. They're just slightly different because EMF is what's being provided and PD is what's being used. Let's do some questions now. Which of the following is a unit of potential difference? Joule per coulomb, coulomb per joule, watt per coulomb, or coulomb per watt? If we go back to the formula for potential difference, we see that it is in fact joules per coulomb. So A is the correct answer. The amount of charge flowing through a cross-sectional area of a wire per unit of time is called voltage, power, work, or current. And we know that current is the amount of charge per unit time, and that matches this definition here. So this one is D. A charge of 2 microcoulombs moves between 2 points in a circuit, and 8 microjoules of work is done. What is the potential difference between these 2 points? As I mentioned with the voltmeter, that's what we're trying to do when we find potential difference. We're trying to find the difference of energy between 2 points. And we know that V is equal to the work done over Q. And the work done here is 8 microjoules, which is 8 times 10 to the negative 6 joules. And we know the charge is going to be 2 times 10 to the negative 6 coulombs. And that gives us an answer of 4 volts. So the difference in potential energy between those two, electric potential energy, is 4 volts. A current of 5 milliamps flows through a conductor for 3 minutes. How much charge is passed through the conductor? So we're going to have to watch our units here. We have 5 milliamps, which we know this tells us that the current is 5 times 10 to the negative 3 amps. And we have 3 minutes, but for time we don't want to use minutes, we need to convert that to seconds. So it's 3 times 60, so we have 180 seconds. And then the amount of charge passing through is what we're looking for. So the equation is I is delta Q over delta T. So we have delta Q is equal to I delta T. So the charge passing through is going to be 5 times 10 to the negative 3 times 180 seconds, which gives us 0.9 coulombs of charge. In summary, potential difference is the work done in moving a unit positive charge from one point to another. Current is the rate of flow of charge measured in amperes. Conventional current is the flow of charge from positive to negative. Voltmeters measure potential difference and ammeters measure current. And the key idea here is that potential difference, this is related to the energy of the particles, the charge carriers. And the current is related to the number of charge carriers. So that's the most important point of this video. And that's it for potential difference and current.